starting today, what we'll do is we'll go to chapter 2, which is two body motion or two body problem. Okay. On Friday, we'll redo what we did on Tuesday. Friday 2 to 3. We'll repeat. We'll have a recitation of what we did on Tuesday. Friday is tomorrow. Alright, let's try to understand this. Now, when we're talking about orbital mechanics, you have to understand the context a little bit. For a long time, what we have tried, or what people have tried is, we have tried to understand the motion of celestial bodies, right? Motion of planets, motion of other stars with respect to something. And the first mathematical representation, the first mathematical laws which mathematically describe the motion of these celestial bodies were Kepler's equation. Right? After that, Newton came along and described his universal law of gravitation and his three laws of motion. So what we are going to derive here is, we are trying to understand, so this is body 1, M1, so this is body 2, M2. So think about Earth and Moon, Earth and Sun, things like that. Alright, so this is our inertial reference frame, okay, the origin at O. Now, the body 1 has mass M1, body 2 has mass M2. The position vector of body 1 is R1, okay. The position vector of body 2 is R2. the position vector of body 2 with respect to body 1 is small r. So r is what? R2 minus R1. Is this clear? If you look at this thing, you can make it out. R1 plus small r is R2, right? Law of parallelogram. So R2 is this small r is R2 minus R1.
And you said small r is position of R2 with respect to R1.
Right. Position of M2 with respect to M1. So mass 2 with respect to mass 1. And this is the unit vector in that direction. It defines the direction of M2 with respect to M1. This point is simply CG or the center of gravity of these two system of bodies. Yes.
Is that supposed to be the magnitude R?
Huh?
Is it supposed to be divided by the magnitude R?
This one?
Yes.
Yes.
Okay. How do you distinguish the magnitude R?
Underline.
The magnitude of
Yeah.
the two.
The scalar is always a magnitude. If there is no underline, it is just a scalar or magnitude. Okay? You can call it a scalar. It is just, what is this R? Huh? What is it in, if you were to explain it in plain terms? It is the distance between these.
Is that position?
Huh?
Is that position?
This R, small r is distance between these two. Does distance have a direction? No, right? So this is that distance. So this means magnitude. So this R is vector. R with underline is a vector. Vector always has a direction. So what is the direction of that vector? From this, the center of this to center of M1 to center of M2. This is the center of mass of these two systems. And Rg is the position vector of that center of mass. Okay? So you take two systems.
You said RG?
Rg.
Oh, okay. That's what?
That's the position vector of the center of mass. Okay? So you have R1. How do you express R1? You can express R1 as x1 I plus y1 j plus k. R2 as x2 I How do you define the center of mass of any system? It is M1 R1 plus M2 R2 divided by M1 plus M2. This is a general definition of center of gravity, right? This is what you have learned. You remember? From statics. This is a general definition of center of gravity. So your Vg would be what? M1 R1 dot plus M2 R2 dot. And Vg
She's saying it the same.
M2 R2, right? So you have, this is how you define center of mass, and if you take the derivative of center of mass, it would just be expressed as rg dot, it would be the velocity of the center of mass. That will be equal to, see, m1, m2 are just constants here, right? You have to recognize that.
That's
M1 and M2.
Huh?
That's DA or R.
This one? Rg,
That's RG.
right. G, capital G,
All the calculations. And the same thing with the okay.
You said M1 and M2 are constants,
m1 and m2 are constants, right?
and VG and AG is velocity and acceleration.
Yes. Vg is the acceleration of the center of mass. Sorry, Vg is the velocity of the center of mass. Ag is the acceleration of the center of mass. Now, let's apply Newton's.
Isn't R dot means R derivative?
Right, R prime or R dot is the derivative, the time derivative. It's very specific that it's time derivative. Okay?
So can you show like how to do it?
Huh?
Watch
How do you take a derivative?
the time.
Yes.
So what do you have here? See, if you look at this, guys, if you look at this, what is changing? What is, if you look at this figure, what do you understand? The position is changing, right? The only thing which is changing here is the position. So if that changes, what changes? R1 changes, R2 changes. Right? R1 and R2 are the only, RG is just something abstract. There is no, it's not physical, it's not tangible. So if you want to figure out how this RG is changing, you have to just take the derivative of R1. R1, you can actually say R1 is R1 of t. Okay? But M1, is it M1 of t?
No.
It's not a function of time. It is just it's just M1. Okay? So that is the reason, if something is a function of time, how does it, if you take this means that Vg just means equal to d over dt of Rg. Right? So that means M1 into R1. You can, how do you take the derivative of this? Do you apply quotient rule here?
No.
You don't apply quotient rule because M1 and M2 are just constants. You can just take that out. Again, it will be just M1 into R1 dot plus M2 into R2 dot. Okay? So now let's apply Newton's law of universal gravitation to M1 and M2. So what we're going to do is, we're going to define, let me do this. We have M1 and M2. Okay. F12 is the force in that direction, F21 is force in this direction. Okay?
Now the direction of those two that you just wrote, you just selected that, right? That's,
Right, absolutely. So that is based on, completely based on this UR. How I define this UR. You cannot define this F12. F12 is what? The force of attraction on 2 because of 1. That is in this direction. That has to be in this direction, right? The force of attraction on M2 on M1, or because force of attraction on 2 due to 1 would be in that direction. It's pulling. You see it? Similarly, F21 is in this direction. F12 and UR are in the same direction. So that is the reason you see a positive sign here. Okay? F21 on the other hand is in the opposite direction. That's the reason you see a negative sign here. This is negative sign.
So it's just the reference that I was doing, right? If you take like this one to be positive, that was negative, right?
No. That's what. This UR, how you define UR,
Okay. So if
UR is defined in that direction.
Oh, that's okay.
Okay? So it is based on UR. It's completely based on this UR, how you define this UR. UR is the unit vector from M1 to M2. So notice Newton's second law. So what I've done is I've replaced this F12 by this. Okay? This is Newton's, yes, mass times acceleration. F21 with this. The right hand side remains as it is.
Because that's the force also. Because that's force also. Yeah, I know.
No, this is
right. The left hand side is mass times acceleration.
Is that R double dot?
R double dot. It's acceleration, right?
Yeah.
Now, what is M1 R double dot, R1 double dot plus M2 R2 double dot?
F1 plus F2. Yeah, F1 plus F2.
This is a very important result. Okay? If you just look at these two, if I add these two, the right hand side will go to 0. Okay? What does this mean?
This can't do it.
The
Look at this and look at this. Okay? Can you say this is the center of mass? The acceleration of the center of mass is 0. Can you say that?
Acceleration.
No, I don't see it. Because of
Compare these two. Okay? This is how we define the acceleration of center of mass, right? If I substitute 0 here, doesn't that mean M1 R1 double dot plus M2 R2 double dot is equal to 0?
Yes.
What about the denominator?
The denominator will just multiply and the whole thing will be 0. Right? You see that?
Yeah.
So if I substitute this equal to 0, the denominator doesn't matter. So what that means is, this acceleration of the center of mass is 0. we have proved that acceleration of center of masses of two bodies is 0. What does that mean? Huh?
They're moving at a
That's
constant
all
speed.
Huh?
Can't force.
They're moving at a constant speed.
So what is it? What is something moving at a constant speed?
They're not attracting each other.
I'm just gonna go acceleration.
See, how did we define the inertial reference frame?
Something that's non-accelerated.
Does not accelerate. This point is not accelerating. Okay, that is an inertial point. It is not accelerating. See, we really don't know this O, where this O is. Right? But what we have done is, by using this, we have actually defined a point which is non-accelerating. So that way, a frame, if you attach a frame to that point, you have found your non-accelerating frame. And you can now solve all your Newton's laws of motion in that frame.
And so the point where it's not accelerating, you're saying is at the center of gravity?
At the center of mass or center of gravity of these two.
Okay.
If you take these two as, what is this? You can also see, if you take these two objects, there will be a center of mass for these two objects, right? You able to see it? And take any two objects, any two of those things, it will have a center of mass or center of gravity, whatever you want to call it. That is the center of gravity. And that center of gravity is a non-accelerating point. So if you attach a reference point or reference frame to that, that frame will be an inertial reference frame. And we can apply Newton's laws in that reference frame.
That 0 underscore is what it means by extreme.
Yes, it means, see, if you add two vectors on the left hand side, the right hand side is a 0 vector. It has to be a 0 vector. You have to make sure you represent that as a 0 vector, not just 0. Okay.
One last question before you raise it. So you said we can count that as the reference point. What do you mean by that? That very last part you said. Could you explain that more? We know that the CG is the point where it's not accelerating.
So if you attach a reference frame to that, if you attach this to that point, that frame would be
The inertial reference frame.
inertial reference. That would be a non-accelerating frame. And you can solve, does this change for two given bodies?
Yes.
Huh?
Two different bodies.
For two given set of bodies, for example, let's say this is Moon and Earth. Does this center of gravity change?
I said yes.
No.
These two are actually revolving around that center of mass. You think that this is these two bodies, the Sun and the Earth and Moon are Moon is revolving around Earth, right? You always feel that, but they are actually, both of them are revolving around or rotating around this or revolving around the center of mass. Okay, I'll get to you why we feel that something is.
So that also implies that they are not, like, even though they are like tracking each other, but they're not like moving each other because they're attracted, right? So
This is attracting this is attracting this.
and both are cancelling each other and they're
So they are kind of rotating like this.
So they're dancing in space.
Huh?
So they're dancing in space.
So one for
I saw that. Yeah, I didn't see that.
I see that.
Alright, we'll keep this figure for now. Okay?
That's it?
See, you have to recognize one more thing here. What is this? You understand what is this? Huh? What is this quantity? What is this quantity? What is that quantity? What is it called? Force is this. You cannot equate those.
Oh,
You cannot.
gravitational.
No, this is force. Force is force. What is this quantity? This is change in linear momentum, right? So force, applied force will result in change in linear momentum. That is Newton's second law. So this is what? This is m d over dt of m1 r1 dot is equal to f, right? The left hand side is change in linear momentum. The right hand side is force. You cannot just, don't substitute. These are two different quantities. This is a law. Okay? So what does this mean? This is the change in linear momentum of what? Of the center of mass. This is the change in linear momentum of center of mass. The change in linear momentum of center of mass is what? Is 0. That means linear momentum of any two-body system is conserved. What is conserved? It's constant. It's not changing. So what that means is this d over dt. In mathematically, what it means? The derivative would be 0. If something is constant, the derivative will be 0. So what we have proved here is, what do you hear? You hear that linear momentum is always conserved. What are the three conserved quantities? Huh? Mass is, you cannot say mass is quite conserved. You say linear momentum is conserved, energy is conserved, and angular momentum is conserved. Okay? So what we have proved here is what? That linear momentum is conserved. This also says that linear momentum is conserved. You see that statement? Do you see it or not? Not quite? Now, yes.
Wouldn't the mass have to be outside of the parentheses? Why are you allowed to put the mass inside the parentheses with the derivative?
It doesn't matter, right? So if you take the derivative, if it's a changing quantity, the derivative, the mass derivative will matter. Because we are dealing with non-changing mass, this can come outside. Does it matter if I write it like this or like this? That's what your question is, right?
Yeah. Oh, they say the same thing.
It's not same thing. See, this is a special case. I told you. This is the Newton's law. The complete Newton's law is this. Okay? If you really take the derivative, you are going to get something like this. If I take the derivative, you're going to get this, right? M into derivative of R plus R into derivative of M. We mostly consider this to be 0. Why? Because mass itself is not changing for most bodies. But when you're considering launch vehicles, rockets, mass is actually changing. So that time this, you cannot apply this law. You cannot apply this law.
We were talking about rockets.
We are talking about rockets.
And what are we talking about now?
Now we are talking about, we've assumed that M1 and M2 are constant, are not changing. Okay?
If two body attract each other, why don't they fly?
Huh?
Two body attract each other, why don't they
We'll get to
fly?
that. You'll understand why we don't do that. Now, you can write R1 dot, R1 double dot is equal to G M2 over R square U of R. Okay. Or so this is from this. Okay. So what I did was M1 cancels, correct? M2 cancels. And if you substitute what is U of R? U of R is vector R over R. So that R into R is R cube and we have vector R. Okay. Now, just think about this. We'll operate under the assumptions. So let's define, we are at a point where we define the two-body relative motion statement or problem. Okay. We operate under the assumption that see, if M1 is really bigger than M2, right? If you're talking about Earth and satellites, which is the case, satellites are much smaller, right? So that time M1 is really greater than M2. And you also assume that M1 is spherically homogeneous. What does spherically homogeneous mean? It is, the mass is equally distributed, right? It can be treated as a point mass with all the mass situated at the center. Okay? So if this is the case, see what happens if this is really big and this is really small. Where does this
CG is closer to the
CG will be the center of this one.
Say it one more time.
If this M1 is really big compared to M2, so this symbol means M1 is really big. Okay? This CG will be the CG of the larger body. Got it? Now do you get it? Why you feel that something is rotating around? If let's say, if the center of mass is somewhere here, right, for these two bodies, if this is really big, this center of mass or center of gravity will move towards the larger mass, the center of gravity will be practically, if this system did not exist, where would the center of mass be?
At the center of the mass.
A bigger one, right? If you add something small, really, really small, right? You talk about Earth and satellite. Does that change the center of mass of this?
Not significant.
Not significantly, right? So that is the reason even for Earth and Moon is considered to be really, really small in comparison to Earth. So Earth-Moon system, that is the reason you feel that Moon is rotating around Earth. But in reality, they are both rotating about their center of gravity. Particularly for satellites, this becomes even more relevant. Okay? So what we have done is, we have defined the center of Earth as a inertial reference frame.
The center of gravity of Earth,
Center of Earth.
not this. Okay.
Because this center of gravity has moved to the center of Earth. This is really, really small. Okay? So what we have done is, a frame attached to center of Earth will be an inertial reference frame.
So when you mean frame, you mean actually taking that.
Right. If you attach this to center of Earth, if this O is at the center, and if it is not rotating along with Earth, the important aspect is, it is not rotating. This frame is not rotating with respect to Earth.
So
It is just attached and yes.
So in a normal, like, let's say just a visual model of a solar system, that will be the sun.
That would be the sun. Yes. So if you're talking about sun and Earth, sun is really, really big compared to Earth. Okay. So the center of mass of the Sun-Earth system would be practically at the center of sun.
And if you made it bigger, that'd be the center of the Milky Way, and you just keep going and keep going.
So we don't go so far. We only go to solar system. We want to see Newtonian mechanics is good within a solar system. If you go really far, it becomes relativistic mechanics.
So when you say that the frame attached to the Earth, what is this frame?
We'll talk about that frame. It's just a coordinate system attached at the center. You understand coordinate system?
Like what you wrote on that.
Right. These.
So it's not an actual thing. It's just
It's a coordinate system. You can actually, if you want, you can go and attach a coordinate system. If you can get to the center of the Earth.
Alright, so what happens if the object passes?
To you. So you're saying between two bodies, one gets larger and the center of mass gets close to a larger object. I'm saying between two bodies, if one body gets like larger than the Earth, the center of mass gets close to the center of Earth.
Yes. That's a three-body problem. No, see, I think this itself will get pretty complex. So I would say digest this, then we'll do the three-body problem. Huh? You're ready? No, you're not.
Believe in the brother.
Alright, so what we'll do is, we have already defined this, right? This is minus G M1 See what happens if the mass is really, really big. Can we assume this implies that we can just go with M1, or this implies M1 plus M2 is equal to m1. We are not really so keen on m2. You understand? So you have this. This will assume RQ. This will be minus G m1 over RQ. So this we use this symbol. See, mu. This will be double dot equal to minus mu over Q into R plus mu over Q is equal to 0. This is the statement of two-body problem. Okay. When we're talking about two bodies, what are you interested in? What are you really interested in?
Are they related to one another?
Huh?
Are they related to one another?
Are they related to one another? You are more interested in figuring out where it is, right? See, what we have always wanted to know was, you look at way behind. We are always interested to know where it is, where these bodies are, where these planetary bodies are. Okay? So this defines, what is this R? That small r, what is it? What did we say that R is?
So the distance is
Huh?
Between M1 and 2.
R underscore. The vector R. What is vector R?
Distance from that one.
Distance, or it is position vector.
displacement.
It is position vector. Okay? It is not displacement, it is not distance, it is the position vector of M2 with respect to M1.
What is,
Right?
what is that symbol? So, okay, so under that second line, there's like a little symbol.
This one?
No, right above that. That little,
G.
no, that.
This one? Mu. This Gm is nothing but mu. See, we have replaced two constants. G is constant, right? M1 is also constant, right? We replace two constants with another constant, mu. So this two-body problem is always defined for two given bodies. Now, if you're talking about Earth and Moon, right? This mu is different. You understand? Because this G and M will change. If you're talking about Sun and Earth, this mu is different. But given, it's only a property of this mu is only a property of what? It's only a function of, but it's a property of the center body only. Whether you talk about Earth, Moon, Earth satellite, Earth space station, this mu would be only a function of that function of Earth. Got it? Right? Similarly, if you're talking about Sun and any other planet, this mu will only be constant, or it will only be a function of the Sun. You see it? You see it in this equation or not?
You said that mu will be constant.
For is a property only of the center body, only of the larger body. Okay? So mu will not change for Sun and Earth or Sun and Mars. If you take if you study Sun and Earth, Sun and Mars, mu will not change for that. Because the center body in both the cases is Sun. If you take Earth, whether you study Moon, motion of Moon, motion of any planets, motion of space station, that mu will not change.
But of a smaller body it will. But of a smaller body it will.
Wait, so what's the example where it will?
Huh?
What's the example where it would change? You're saying like the sun, the earth, and the moon
Right.
would change?
If you're we only study, when we study two body problem, we study two bodies at a time, right? You don't study sun, earth and moon together, not yet. That is a three body problem. You got it? This is, see, we are specifically interested in a two body problem for now.
Right.
So it's safe to say that only mu changes in three body.
No, if you're studying sun and earth, if you're studying earth and moon, okay, what is the center body for this sun and earth? Sun. What is the center body for earth and moon? Earth. Right. This M1, in the first one is sun, in the second one it is earth. That time mu changes. If you're studying sun and earth, sun and Mars, mu doesn't change.
Because they're both large.
Huh?
Because they're both large.
No.
They're both.
What is the center body in both? Sun and earth, sun and Mars. What is the central body?
Sons.
Sun. This M is M1 is sun in both the cases. So the mu will not change. You guys cannot use your cell phones, okay? Gentlemen? No cell phones. Because see, this course is difficult as it is. If you are not going to pay attention, it's going to be even more difficult. I know many people are getting lost already. This is just to second or third class, but so please pay attention. Whatever you can grasp it. Alright?
What if we study like Earth and Mars?
Can you study Earth and Mars?
It would be like
Huh?
Isn't Mars slightly smaller than Earth?
Huh?
Isn't Mars slightly smaller than Earth? Or is it vice versa?
Like, I mean, what I meant to say, like, if you study like two equally, like equal mass,
You have to think about this. See, there is, if you talk about Earth and Mars, you cannot ignore Sun.
Oh, because you can do Earth's moon because the moon is actually going to
Right. The gravitational effect of Sun on Moon is negligible compared to the gravitational effect of Earth on Moon. You understand? You cannot study Sun and Moon by ignoring Earth. You cannot study Mars and Earth.
so we're not studying two planets.
It's not two planets, but think about what is revolving around what. Right? So you have to think about that. If Mars was revolving around, see this, when we talk about this, we talked about this forces, right? This force of attraction, there is obviously force of attraction between Earth and Mars as well, okay? But the force of attraction, we kind of ignore the force of attraction between Earth and Mars when we study Sun and Earth. It's called third body effects. When we study Moon and Earth, we ignore the effect of Sun on Moon, other planets on Moon. Got it?
Yes.
We say it is negligible.
So anytime, so in order for mu to not be constant, something would have to be bigger than the sun. I'm still waiting on that condition. My question is, what is the condition when mu is not constant?
We are studying two bodies at a time, right? If the central body in these two bodies is the same, mu remains the same.
Right.
If you're studying, you can study Moon and a satellite orbiting Moon. So that will be, this mu will be that time related to gravitational attraction of Moon and the mass of Moon. You understand? Every object has a gravitational attraction. Even we have gravitational attraction. Right? You can, if you want, you can study even asteroids. There are satellites orbiting asteroids out there. They have gravitational attraction.
So for a black hole, is a
And that's different mechanics. Alright, so this is very important, okay? As this, we'll use this equation a lot of times. This is a statement of two. So what is the statement of? Two body relative motion problem. Why is it relative motion? It's motion of body M2 with respect to M1. That is the reason we call it relative motion problem. Okay? Statement. This defines the statement. This is a second order. Do you recognize this as a second order non-linear differential equation? Okay? You do? That's our double. Okay. So what we have done is we have already proved that linear momentum is conserved. Okay. So let's look at angular momentum. How did we define angular momentum? Huh?
Momentum caused by rotation motion.
There's no force in the tangential force.
Angular momentum is R cross mv, right? What we do is in orbital mechanics we define something called specific angular momentum, which is simply angular momentum of the orbiting body with respect to the central body. Okay, and this is per unit mass. Okay, this is defined as specific angular momentum, and we'll use only specific angular momentum.
H2 over A.
Hmm?
H2 over A or H2 over A?
It just means angular momentum of body 2 with respect to 1. It's just a notation. Huh?
It's the same thing what we tell
Hmm?
the slabs on this one.
So this is specific angular momentum. Okay. Recall two body problem statement, which is R double dot plus mu over R cube and R cross U. Alright, so what we did was, so look at this, it's fairly simple actually.
Says the man with the PhD.
Hmm?
Says the man with the PhD.
So we define, this is angular momentum, okay? We define something called specific angular momentum, which is small h. It's simply R cross V. We will not be using V and A. Our V would be what? R dot. What will be our AB? R double dot. So this is A. Okay. So this is how we define specific angular momentum. Angular momentum per unit mass. Now this is our two-body problem statement, right? Two-body relative motion problem statement. I took this and pre-crossed this with vector R.
Why?
Huh?
Why?
Because I want to show you that angular momentum is conserved. I showed you, we proved that linear momentum is conserved. Now we want to prove that angular momentum is conserved, correct?
What do you mean by conserved?
Constant.
Okay.
In nature, these three are always constant. Angular momentum is constant. Energies, you have heard the statement, energy cannot be created nor destroyed. So what does that mean? Huh? Transferred from one form to the other. What that means is, it is always conserved. The total entropy of the system is always the same, right? What does that mean? That energy is always conserved.
So how would you know to cross that?
Huh?
Like, how would you know to cross?
That's just, if you do it many times, you can figure that out. Okay? So you free cross this with R, vector R. Okay? Why is this 0?
Because product of same space.
Vector crossed with itself is always 0. Okay? So you have this, and then you have this. See, I can write this as d over dt of R crossed with R dot. Okay? Why? So d over dt of R crossed with R dot is what? You're going to get R crossed with R double dot minus R dot crossed with R dot. Right? Again, this vector is 0. Vector crossed with itself. So you see this one and this one. Or, yeah, this. See this one and this one. So these two are the same. R crossed with R double dot just means d over dt of R crossed with R dot is 0. Right? You follow that? If the derivative of a particular quantity is 0, what does that quantity have to be?
Same.
If the derivative of a particular quantity is 0, that quantity is constant, right? So you can say this is what? This is our angular momentum. Right? So the derivative of angular momentum is, specific angular momentum is 0, which means h is constant or conserved. Okay? We'll do one more thing and we'll stop here.
Right above when you wrote cross the above equation with R. On above, one line. Yeah. Did you cross R twice?
No, I'm just crossing the entire. So what has been done is here it is R crossed with R double dot plus mu over R cube. So it gets distributed, right?
Okay. Okay.
Now, total mechanical is resumed. is also conserved. So how do we prove that? Again, recall.
You mean potential and kinetic?
Yes, the total mechanical energy would be see if you observe actually the total the potential energy and kinetic energy just get transformed into each other. Okay. We have R dot plus mu over R cube. R dot is R. Okay. So what you're going to get here is this is what?
R square.
This is R square. Okay. So you're going to get mu over R. What is this? See, d over dt of
That would be like R dot is square. That would be like R dot is square. Right? Alright, we'll pick this up next class. By the way, who's missing? Thomas, you were missing last class? Anybody missing 1, 2, 3, 4, 5, 6, 10, 3 people are missing. Do you guys know who's missing? Did anybody move up? Jano is moved up. He went out. He's the only one who left and who stepped out. No, he's the only one who stepped out. I'm just trying to figure out the attendance. Anybody else?
Oh, yeah.
Nikki is absent.